Designing the persistence layer for a real-time conversational AI platform means managing a relentless, high-velocity stream of incoming data. That data is not uniform. We process transactional billing records, track live sub-millisecond telemetry, and route massive audio media files. To maintain a natural, fluid conversation, the entire system must execute its read and write operations within a strict, non-negotiable latency budget of under 800 milliseconds. Relying on a single traditional database architecture to handle all three of these tasks simultaneously will guarantee system collapse. The structural requirements for calculating financial records inherently conflict with the speed required for live voice processing. This blank blueprint represents our sandbox. To make this work, we employ polyglot persistence, the practice of combining completely different database paradigms and mapping them precisely to the specific shape and access pattern of the incoming data. Adulting at a global scale requires abandoning the search for one perfect tool. Instead, we must orchestrate multiple highly specialized storage engines without violating that strict 800 millisecond time budget. The first layer of our architecture is the control plane. This handles user accounts, API keys, and system billing. Billing math requires absolute correctness over raw speed. A dropped zero or duplicated charge is catastrophic, making this the highest stakes workload in the system. We anchor the control plane with a relational database like Postgres. It provides A-siege guarantees, treating multi-step operations as a single transaction. A stands for atomicity. All steps must complete at once. If the final step fails, the process immediately rolls back to zero. The C stands for consistency. Once data is committed, it is instantly visible, ensuring constraints are never violated. We willingly sacrifice sub-millisecond query speed here. Financial integrity demands the rigid, schema-defined safety that only relational tables provide. Leaving the billing layer, we pivot to the high-velocity requirements of the real-time audio stream. Maintaining live session state in a relational database requires matching and joining multiple tables together. That calculation overhead is far too slow for an active voice loop. To solve this, we place a key value store directly in front of our database. This cache handles per-node telemetry, bypassing the relational structure for sub-millisecond retrieval. We also introduce a document store. Variable, unstructured AI transcripts map perfectly into these flexible, JSON-like document collections. By utilizing NoSQL, we drop the rigid schema and ACID guarantees of the relational world in exchange for flexible records and lightning-fast query execution. The architectural split is highly deliberate. We map rigid, predictable schemas to the money layer and schema flexibility directly to the speed layer. Physical infrastructure introduces a harsh reality. Network partitions and communication failures are inevitable. Eric Brewer's CAP theorem states that during a network failure, a distributed database cannot guarantee both consistency and availability. It must choose only one. When a network bridge fails, the Postgres control plane operates as CP, consistency over availability. An API check hits a hard error. The system halts intentionally to prevent stale billing data. Conversely, the telemetry cache operates as AP, availability over consistency. The request is served immediately, keeping the connection alive even if data is temporarily stale. Breaking the real-time audio loop with a hard error drops the user's call entirely. In this specific layer, serving slightly outdated telemetry state is vastly preferable to dropping the connection.
Advanced architecture cannot prevent hardware failures.
It is the practice of consciously engineering exactly how different data layers will behave when the network inevitably breaks. We still have to account for our final data type, unstructured, massive binary large objects, or blobs, such as the rendered audio recordings of user calls. Attempting to force massive audio files into rows of a standard database will bloat the storage limits and crash the entire query engine. Back on our blueprint, we implement an S3 object store. This abstraction provides flat buckets designed for HTTP REST access, acting as an independent media plane. Cloud providers separate massive storage into tiers. We use hot storage for recent audio and cheap cold storage for archiving. An automated lifecycle rule shifts aging audio out of hot storage, dropping it into Glacier for long-term retention. By physically separating these unstructured media payloads from our operational metadata, we achieve infinite scaling capacity for the audio files without bottlenecking the core database. Even with distinct database paradigms perfectly matched to their data types, high traffic volume will eventually saturate the nodes and threaten that strict 800 millisecond latency budget. When vertical hardware upgrades max out, we scale orthogonally, applying distinct distributed techniques at the exact same time. First, we use indexing. By building hash maps or B-trees within the database, we provide sublinear lookups. The database instantly locates the requested record, rather than executing a sluggish full table scan. Indexes require extra storage space on the disk and marginally slow down new write operations as the index updates itself. Second, we introduce replication. Looking at the blueprint, we copy the entire dataset across multiple identical replica nodes. These read replicas absorb the heavy querying traffic generated by user dashboards, taking the load off the primary database, while simultaneously eliminating any single point of failure. Making individual nodes search faster with indexing, while copying those nodes for safety through replication, builds the necessary foundation to absorb massive traffic spikes. A massive, unpredictable spike in traffic from free-tier users can easily saturate the shared CPU and memory of the cluster. Shared hardware congestion directly threatens the strict 800 millisecond latency guarantee we owe to paying enterprise customers. To prevent this, we introduce the third scaling technique, partitioning or sharding. Here, the heavily saturated cluster physically splits into entirely separate infrastructure paths. Unlike replication, partitioning splits datasets across separate machines, establishing strict tenant isolation. By assigning enterprise customers to dedicated shards, chaotic free-tier congestion remains physically trapped on its own infrastructure, safely behind the partition line. True horizontal scale moves the objective from simply absorbing larger datasets to mathematically guaranteeing performance boundaries between different classes of users. Reviewing the complete architecture, we see incoming data routing cleanly to its specialized environment. The billing records land in Postgres, the telemetry hits the key value caches, and the massive audio files route directly into S3 object storage. Billing stays strictly consistent. Telemetry prioritizes absolute availability, and media relies on flat, infinite blob storage. Underneath it all, the orthogonal layers of indexing, replication, and physical partitioning protect the core infrastructure from collapsing under heavy global load. Optimal system design is the process of defining the boundaries of your data, its schema, its scale, and its failure tolerance. From there, it is simply a matter of engineering the exact mathematical trade-offs that are required to meet your performance reality.